quería hacerles simplemente, aprovechar que están todos acá para hacerles un comentario. Recuerden que la aprobación del curso está vinculada con la presentación de un proyecto que aplique las técnicas que están mostrando el profesor Sodré y Vitor. Como creo que ya les comenté o por mail o el lunes, tanto Laerte como Vitor están completamente disponibles para que ustedes los consulten sobre esto. En los próximos días, por ejemplo, podría ser durante la mañana, ya que a la tarde, jueves y viernes todavía tenemos el curso, o la semana que viene, lunes, martes y miércoles, durante todo el día. Entonces yo les envié por mail los emails de Laerte y de Vitor. Entonces siéntanse libres de contactarlos y de plantearles cualquier duda que ustedes tengan, y también para coordinar, para acercarse a las oficinas de ellos, a consultarlos. Y también yo reservé para los 3 días de la semana que viene la sala de reuniones del IALP entre las 2 y las 4 de la tarde, por si había varias personas interesadas en discutir los proyectos con el profesor, que me parecía que quizás era más cómodo que hacerlo en la oficina, si se genera un grupo de personas con intereses en distintos proyectos. Así que, como les digo, o sea, la idea de este curso es que ustedes lo aprovechen lo más posible, y que aprovechen la presencia de Laerte y de Vitor acá en la facultad hasta el miércoles 7 de diciembre. Y insisto, ellos están completamente dedicados, con tiempo disponible para que ustedes los consulten sobre cualquier inquietud que tengan sobre los proyectos o Machine Learning en general, o si están interesados en hacer los ejercicios de la práctica, consultar sobre eso, ningún problema. Así que nada, solo ese comentario, y lo dejo entonces a Laerte a cargo de la clase. Decime, sí. ¿Se puede hacer en grupo, Laerte? Sí.
No sé, creo que
Sí,
sí, porque es
sí,
más fácil.
podría ser,
Sí,
sí, sí, sí. Porque sí, para alguien que empieza recién, en tan poco tiempo, quizás pueda ser también más ameno, o que abra un poco a la discusión, ¿no? Sí, 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 podría ser en grupo, tranquilamente. Así que, bueno,
ok.
Laerte.
Buen día. Ah, bueno, hoy voy a hablar específicamente de lo que es Machine Learning. Ustedes van a descubrir que conocen ya muchas cosas de Machine Learning, pero con otro... Oh, sorry, I was speaking Portuñol. Uh, you will discover that you know a lot already about machine learning. But what happens is that the names of the things that we use in general in physics and in machine learning for the same thing are different. For example, learning in machine learning corresponds to optimization in physics or other branches of the hard science. But I will explain it to you soon. So today I will cover the general ideas around machine learning. In this plot at the right, I show you what is the difference between artificial intelligence, machine learning, and deep learning. Actually, artificial intelligence is the general name of an area uh, that is developing very fast, and it comprises machine learning has a sub-area, and deep learning is a sub-area of machine learning. Okay, so deep learning is also machine learning and is also intelligent artificial intelligence. Uh, you saw probably a file that I sent to Analia with a number of papers that appeared recently in AstroPH. I suspect that there are at least, well, you know, in AstroPH, when you sign for a given area, you receive papers of that area and some cross correlated papers. And I suspect that we have about 3 papers that use machine learning per day in AstroPH. In the figure in the left, you can see the relative frequency of papers. And here is one, okay? And these papers are normal, the number of papers are normalized by the sum of papers on extragalactic astronomy and cosmology. They represent the slide 1. And you can see along the years how fast several areas of artificial intelligence are being used in astronomy. For example, we show here in red papers that use neural networks. By the way, the first paper using a neural network in astronomy was published in 1992. During a long time, there were very few papers on the subject for reasons that I will show to you probably tomorrow or the day after tomorrow. But since in this millennium at least, we can see that after 12, 15, we are seeing an explosion of the papers. And you can see also papers that use Bayesian methods. They are increasing very fast. So this is a growing area of astronomy. And one of the main reasons for that is the enormous amount of data that has been generated already by several astronomical projects like Galaxy Surveys, Gaia, etc. And that are expected in the next years with, say, LSST and the other large projects. And you can see that we have a growth that is essentially exponential in the data volume produced by surveys or other instruments. And what makes machine learning in general useful is that its ability to deal with large amount of data. This is one of the reasons why we see this exponential growth in techniques associated to machine learning. Okay, let's start by comparing what is machine learning with respect to conventional computation. You all know conventional computation, I suspect. Let's consider a simple problem, a classification between star or galaxies from a table generated by the analysis of an astronomical image. Okay, when we do classical programming, we establish a sequence of rules or algorithms that the computer will run to solve a task. Probably most of you know already a software called Sextactor. That is the most used software for image analysis. Sextactor it runs over an image line per line and identify pixels with intensity above the mean and ascribe pixels above the mean to objects. So it builds catalogs of objects, measure the properties of these objects, and among a lot of other things, they evaluate a parameter that we call stellarity of an object. That is essentially the probability of an object being a star. Sextactor is a program written in C++. Machine learning, on the other side, has a completely different approach. we call machine learning the kind of systems that learn directly from the data without being explicitly programmed for a specific task. I mean that a specific machine learning algorithm can be used for lots of applications, not just for one specific application. So I adapted a figure from Chollet's book. I will talk about this book later, where we can see the difference between classical computing and the machine learning. In classical computing, in general, we use the rules that are used in the program. We feed the program with data and obtain answers. In the case of machine learning, we have two stages. In the first stage, that is the training of the algorithm, we provide to the algorithm the data and the answers that we already know. For example, if I want to classify star or galaxies, I give to the algorithm parameters of the objects, the data, and the answers, whether the object is a star or a galaxy. By doing that, the algorithm will be establish its own rules. We will see how. And in the second stage, the inference stage, we use the rules and the data to provide the answers with the same algorithm. Well, a very common problem in astronomy and the physical sciences in general, the estimation of a variable y from a set of the other variables x. We can write this inference in this way. Y is a function of x given a set of parameters that characterize the function. Here I'm writing very in the simple way, but either x or y can be scalar, vectors, tensor, images. The things that enter here can be very complex. What machine learning does is to promote a mapping between x and y. You know, a mapping between x and y is what we call a function. So machine learning actually, at least supervised methods, they implement a function. Functions in general have parameters. For example, if I am fitting a straight line to a data set, we have two parameters, a and b, for example. Y equal a plus bx, for example. I will call w the parameters of a model. And what we call learning in deep learning is the determination of w. You know, in physics, in general, we call this sort of problem model optimization or parameter inference. But in machine learning, exactly the same two kinds of problems are called learning. And what happens is that different machine learning algorithms implement different functions and learning strategies. I think that is very distinctive in the case of machine learning is the kind of function that we implement. In general, we are used to polynomial functions, trigonometric functions, things like that. But the functions used in machine learning are very different. For example, I'm showing here a decision tree. A decision tree, look what happens. I suppose I have a set of 12 photometers, photometry in 12 different magnitudes, and I feed I feed the data to a decision tree, and these parameters U, Java, F, Petro, F1 are all magnitudes, okay, from the S Plus survey. So if you say U Java magnitude is larger than 0.46, it goes to this side. Otherwise, it goes to this side, and so on. Here, depending on the values of the magnitudes that I feed the tree, it will go and it will finish in one of these leaves. And in one of these leaves, it will be classified as either a star or a galaxy. 0 for star here, 1 for galaxy here. Actually, this is a function, but a function of nature very different from what we know in general, or what we are used to. Okay, the learning process is what determines whether what is the thresholds here, what is the best magnitudes to be used at each stage of the tree. But this is nothing but a function, a very different function. We distinguish between two types of learning, supervised and unsupervised learning. In the case of supervised learning, we know the value of y. I mean, we have input and the output variables, x and y. And the algorithm learns to map x to y, using examples of x of a training set for which values of y are known. So I have a training set for which we have x and y. For example, we know already if an object is a star or galaxy. This is given by y. And I use the y are called the targets. And this is the data necessary for training the algorithm. Knowing the x and y, we can solve machine learning problems. There are two kinds of supervised learning, classification and regression. In classification, y is a qualitative, categorical, or discrete variable. For example, star, elliptical galaxy, detected or non-detected, class 1, 2, 3, etc. While in regression, y is a real number. For example, it can be the redshift, the metallicity, the mass, etc. So you can see that we are dealing with two kinds of functions here. One for that solves problems of classification, and the others of regression. But both falls into the box of supervised learning. In the case of unsupervised learning, we don't have the y. We have the data, and we want to identify structures or interesting properties of the data. This is very useful for data exploration in general. And under this label, we have cluster analysis, density estimation, and dimensionality reduction. Today, in the end of this class, we will discuss these three topics. Okay, another way of considering algorithms of machine learning is by self-supervised learning, for example, reinforcement learning, etc. In the case of self-supervised learning, we try to obtain an answer without, say, human intervention. And I illustrate it with an algorithm called autoencoder. That's a kind of neural network where, looking at this structure, here we have the input. The input could be, for example, an image or a table. For illustration, let's suppose that I feed the autoencoder with, say, a number of magnitudes. And we train the autoencoder so that the output is equal to the input. But notice that due to its structure, the autoencoder has in the middle less, say, nodes than the input or the output. This means that the autoencoder in order to maximize the approximation between the output and the input, should find the better possible compression of the data. So autoencoders are very powerful for data compression, nonlinear data compression. This is a very important type of neural network. In the case of reinforcement learning, we have a completely different kind of architecture. We have an agent that learns actions that maximize success or reward. This is very often used in games, in autonomous vehicles, in astronomy search for outliers, things like that. For example, you probably are all aware of the computer program that won the Go game playing with the champion. This is an algorithm that implemented the reinforcement learning. The motor of learning is gradient descent. How we do the optimization or the learning? We can consider learning, as I already mentioned, has parameter estimation. We need to have what we call a cost function, which will measure how close we are from our targets. Okay, the cost function can be, for example, a chi-square that you are all already know. And what we do is, using a training set, we try to minimize the cost function. This is done iteratively using this algorithm gradient descent that works in this way. We initialize the algorithm with the random values of the parameters, and iteratively we update the parameters in this way. The new W is the old W minus a parameter that we call learning rate times the gradient of the loss function. Loss function or cost function is the same thing. You'll notice that the gradient points towards the distance of the maximum variation of the function. And if we took the negative sign here, it goes to the direction where the function decreases. That's why this appears here. Notice that lambda is an additional parameter. Parameters that are proper of the training algorithm are called hyperparameters. Okay. Here, for example, I am plotting a problem of linear regression where I have implemented this algorithm. I started with arbitrary values of a and b that give this straight line here. In the next iteration of the algorithm, we move to this new line here, and so on, up to when the algorithm is trained, we obtain the best fitting for this data set. Another way to see machine learning algorithms is by the parametric and the non-parametric models. Parametric models are equivalent to the supervised learning that I just talked about. They are models where we have a functional form. The functional form does not need to be something analytical like a polynomial, for example. It could be a neural network, a random forest, things like that. But anyway, we have a set of parameters that the model needs to learn. In the case of a linear regression, for example, we have a parametric form that is the line equation with these two parameters. The prediction of a new observation, suppose that I have a new x, it depends only on W, not on the data. We use the data to obtain W1 and W2, but after we have it, we don't need the data anymore to predict the new values, okay? This is very obvious from this expression. Given an X, I can obtain Y without knowing the data from which W and W2 were derived. So the parameters are estimated from the data, from a training set, and we are then able to do predictions. Again, machine learning implements a function. The complexity of the model in this case is limited. For example, if I assume this parametric form, I will constrain to it. If the data is not well fitted by a straight line, well, we will have better results. This is why we say that parametric models have low flexibility, contrary to what we will call non-parametric models. Although the flexibility of some models, like neural networks or random forests, for example, are very, very large. Non-parametric models. This is equivalent to unsupervised learning. We say that we don't have any initial preconception or assumption about the data. In this case, we have only the data. We don't have a why. The goal is to discover interesting things about the data, and in general, when we are starting a machine learning project, it's often useful to start with an analysis of the data using non-parametric models to know better the data. As you will discover, the most difficult thing in machine learning is not running algorithms or choosing algorithms. It's to prepare the data for the algorithms. Because data in general have problems. Sometimes we have missing values, sometimes we have wrong values, sometimes we have outliers, and so on. And all these things might affect the result of the process. So non-parametric models are very, very useful to explore the data. That's why I think that you should always use you should start your models by running some non-parametric models to look at the data. Since it doesn't depend on any model, they are considered flexible models. They can be applied to models of any complexity. Although we call non-parametric models, this doesn't mean that these models don't have parameters. They do. For example, a very common and very important non-parametric model is the KNN model, the case nearest neighbor. For example, we have a cloud of points and we can estimate the density using this algorithm by computing, say, the number of objects inside a circle, in the case of this example, within the distance of the seventh neighbor of this point. Using this algorithm, for example, we can obtain the density distribution of the points, like I'm showing here. So in this case, I'm using the seventh neighbor, k equals 7. So again, k here is an hyperparameter, okay? But otherwise, we don't have any other constraint to run this type of algorithm. Another very important concept in machine learning is generalization. We use a certain data set for training a model. And then we will apply this model to new data. Okay, I train an algorithm, say, to classify stars or galaxies with a given set of data, and then I want to apply this algorithm to a whole survey. How do the algorithm will behave with this new data? Well, we expect that good models should do good previsions. This is, in the machine learning jargon, we say that these models generalize well. They behave well with this new data. So generalization is a term typical of machine learning, but its concept is very intuitive for us. Is the ability of a model to provide good results. In general, to evaluate the generalization capacity of an algorithm, we divide the data in the training set, in the data available for training, in three parts. One for training itself and validation, and one part of data for testing. For example, we can choose 70% for training, 10% for validation, 20% for testing. And what's important is the following. The test set shouldn't be used at all in training and validation. It should be fresh, so that when the network or the algorithm never saw the data in the test set during the training, of course. The figure is not very good here, but let me show the following. I'm plotting here in red the data points used for training. And in green, it's almost invisible in the screen, but anyway. Here are green points that are used for test. So a good model, it fits more or less well both the train and test data. A bad model, like the blue line here, it fits very well the train data, but very badly the test data. You can see that I'm not sure, but here are some test points that you are unable to see. You can see that this bad model passes very far away from these points. So this blue line is a bad model, a model that doesn't generalize well. Since we use gradient descent optimization, during the training, the loss function or the cost function always decrease during the training. You can see here an example. With the validation set that we use together with the training set, we notice that at the beginning, the loss function of the validation set decreases, but after some point, it starts to increase. What happens is that at this point, the model is overfitting the data, like in the previous case. In the blue here, the blue line, it passes very closely all the red points. It fits very well the train data, but very badly the test data. It's overfitting the test sets and not providing a good generalization. The same happens here. So we consider this point here where the model, the validation set starts to increase again, the loss of the validation set starts to increase, has a sign of overfitting. Before this point, we have underfitting. So this is the optimal point of the training. Here you see I'm plotting the loss function or cost function has a function of epochs. One epoch is when I present to the algorithm all the points in the training set. I do it repeatedly, and in each repetition we can trace these lines. So we need to stop the training at the point where we start overfitting the data. Okay. So, for example, here I have again in red the training data. In green, you can see it probably, the test data, and in blue here I'm the model that I use to generate this data. Here I show the best model. Here I have an underfitting, and here I have overfitting. Notice that the curve here passes over all the trained data, but falls very far away from some of the test set data. Here I'm showing to you some of machine learning algorithms. For example, a very in say I think that 2009, for example, I used the local regression algorithm to estimate photometric redshifts for a sample of SDSS galaxies. This was probably one of the first time that someone used this kind of algorithm in astronomy, but it's the local regression. It uses a window and computes means of y values in the window. In this way, it can trace a function here. Gaussian processes are a very powerful kind of algorithms when we have fixed points. If we have fixed points, Gaussian process is a kind of algorithm where we work in the space of functions instead of space of parameters. They are used also, for example, in regression in problems of astronomy. The KNN and the trees that I have just mentioned to you. A very powerful algorithm, the random forest. Random forest, we have the training data here, and we create subsamples using different sets of features of the data. I mean, suppose that I have a data set comprising the 12 magnitudes of S+. We create, say, different subsamples using, instead of the 12 magnitudes, say 7 magnitudes. And here enter 7 magnitudes, 7 magnitudes, 7 magnitudes. But the magnitudes that enter in each of these different subsamples are different. So in this way, the algorithm is able to find what is the best combination of the magnitudes that will lead to the best results. And each of these different combinations feed different decision trees, and in the end we obtain a result. This is one of the most powerful algorithms known for regression and classification. And before the advent of neural networks, they were with support vector machine, the winners of the competitions between different machine learning algorithms. The autoencoder I have shown already to you, and here is a kind of network that we call convolutional neural network that I will talk to you in 2 days. That is very powerful for mainly for image analysis, but not only for it. Okay, there are many possible applications of machine learning: classification, regression, density estimation, cluster analysis, dimensionality reduction, anomaly detection. Anomaly detection is the same than outlier detection. Time series, information recovery, recommender systems like those in Netflix, robotics and computational vision, games, etc. And there's also a fauna of machine learning algorithms. Logistic regression, that despite the name is a classification and not a regression algorithm. Decision trees, naive Bayes, KNN, support vector machines, that is also very powerful for classification. Random forest and bagging, very powerful for classification and regression. Boosting, neural networks. So now I will talk a bit about density estimation, cluster analysis, and the dimensionality reduction. They are very useful as tools for discovery of structure in the data. As I mentioned already yesterday, in the data space, the data forms structures, and one of the most interesting things that we can do is to try to find structures in the data space. This is also used for visualization and data description. Okay, let's consider, for example, density estimation. Our objective here is to model the data distribution in the data space. Say, obtain the probability density function of the data. For example, I have here a color diagram, and using algorithms of density estimation, I can model this data set with the sorts of functions here. This is a kind of non-parametric. We can have both parametric and non-parametric algorithms to do that. One example of parametric algorithms is the Gaussian mixture models, GMM, that Vitor will talk to you later. These models, we model the data distribution has a superposition of several Gaussians with different means and variance. And we can evaluate the number of Gaussians, for example, to be used using model comparison. For example, the Bayesian information criteria or the Laerte information criteria that are often used in machine learning algorithms to evaluate the quality of the models. For example, here I'm showing in the case of this example, the number of Gaussians and the big value. Actually, here is minus the big value, okay? And you can see that the big value that compares that gives the complexity of a model, it is maximized in this case with 3 Gaussians in the case of this specific example. Another important way to estimate density is using kernels. If we have a data point x in a d-dimensional data space, we can define the probability density function in this way. It depends on the number of data points, of a parameter that we call bandwidth, and the kernel function, and the distance between points, the point where we want to estimate the density, and the points in the training set. Well, the kernel function is a kernel with is a function with limited support, and there are many different forms. For example, the Gaussian, the top hat function, and the Epanyshnikov, etc. the main parameter or hyperparameter of this model is the bandwidth, the kernel bandwidth that appears here. And you know, you have here a distance between 2 points. There are many different kinds of distance, but for the moment, let's suppose that we have a Euclidean distance between the points. So suppose that we have a point here, and we want to estimate the probability density function here. So the kernel will estimate a kind of weighted mean in a region around the point of interest. So you can see that h that appears here, the bandwidth, is a critical parameter of the method. And it can be estimated through a procedure called cross-validation. Cross-validation is very useful in machine learning and is a technique that we use often to estimate hyperparameters. Cluster analysis. In this case, our objective is to estimate, to identify, say, groups or clusters in the data. It's a kind of unsupervised technique where we don't know a priori where the clusters are. So it is different from classification because we don't have a label for any point. We don't have y in this case. So there are two main classes of algorithms for cluster analysis. One is the k-means, Vitor will talk about later, and the hierarchical methods. And let's see how k-means works. Our objective with k-means is to ascribe n objects to k groups. We should give the number of groups. We should give k, okay? The algorithm minimizes, if we use, say, Euclidean distance, this distance. Let's suppose that we have k groups, and mu k is the center of each group, and we will minimize the sum of the square distance of each point to each group this way. The algorithm works more or less like that. We start defining the number of groups. We initialize by choosing k objects randomly as group centers. We ascribe each object to the nearest group. We recompute the group centroid, and we repeat the process till the convergence. In the convergence, the groups essentially freeze. They don't change anymore. For example, in this case, with two groups, we obtain this sort of clustering. Another important application of non-parametric methods is dimensionality reduction. You know, we have in general data in very large dimensions. For example, in the case of the S+ survey, we have photometry in 12 different bands. So the data is a point in a 12 dimensional space. Of course, we are unable to see anything in 12 dimensions. So either for visualization or for understanding better the data, it's useful to try to represent the data in lower dimension. So let's suppose that we have this data x in d dimensions, and we want to represent it in a space with dimension d small, with dimension much less than d. So we want to do a mapping from this space to this space that I'm calling y. This sort of procedure in mathematics is called embedding, when one mathematical structure is contained within another. This is very useful for data compression and visualization. Probably most of you already know principal component analysis. Principal component analysis, or PCA, is a linear method and is probably the most used dimensional reduction methods, but there are also nonlinear methods. For example, LLE, locally linear embedding, isomap, TSNE, very popular nowadays, T-distributed stochastic neighbor embedding. As illustration, I'm showing here the data in 3 dimensions, the S-curve, and here I show what happens if we apply PCA or this other algorithm, locally linear embedding, to summarize the data. You see that we are obtaining representations here in 2 dimensions of the 3-dimensional data that are very, very interesting and very distinct one of the other, but both useful to understand more or less what's going on here in high dimensions. This PCA is so important, I think that it's worth to talk a bit more about it. What PCA does is the following. You have data in a very large dimensional space. PCA looks in this high dimensional space for the direction where the data has maximum variance. This direction is called the first principal component. After defining this direction, the direction of the first component, PCA looks in the subspace perpendicular to the first principal component, and in the subspace it looks for the direction of maximum variance, and this direction then is the second principal component. Knowing the first and second principal component, PCA looks in the subspace perpendicular to PC1 and PC2 for the direction of maximum variance, and this defines PC3, the third principal component, and so on. So PCA is very useful to summarizing data in low-dimensional variables. It's very fast since it can be solved. It has a linear algebra problem, and is largely used in science in general and in astronomy in particular to examine data in large dimensional space by projecting in few dimensions. A problem that I often see with people using PCA is the following. Many people try to ascribe physical interpretation to each principal component. Sometimes this makes sense, but sometimes this does not make sense, because each principal component is actually a linear combination of all the variables x in the large dimensional space. So in some cases, you can say that, the first principal component is associated, say, with the star forming rate of a galaxy. But this is not always true. So I say that you should take care of these physical interpretations. It is not always obvious that the principal components have physical interpretations. But anyway, they are very useful, as Vitor will show to you soon. Another very popular nowadays dimensional reduction technique is called the TSNE, T-distributed stochastic neighbor embedding. It is used mostly for visualization, and the objective, like the other dimensional reduction techniques, is to represent high dimensional data in a low dimensional space. And what TSNE does is to calculate similarity measures between pairs of points in the high dimensional space and in the low dimensional space, using what we call the Kullback-Leibler divergence. That is a measurement of the difference between probability distributions. I'm not a big fan of Disney, I should say, because sometimes it provides very good results, like in this case here. Here is a data set, and we see here PCA results and Disney results using a data set called MINST that we'll see in 2 days. That is a data set of images where each island here corresponded to one of the digits between 0 and 9. You can see that using this technique, the digits are very well separated in this plane of latent variables. These variables here that doesn't have any special physical signification, but are the output of the Disney, are called latent variables. Also, in the case of the autoencoders, the nodes in the center of the autoencoder, that nodes we call also the latent space or latent variables. And the same data with PCA, you can see that everything is mixed here. So PCA is not good as a four-dimensional reduction in the case of this data, for example. I forgot yesterday to talk about some useful reference for you, so I will mention briefly then they now. The first reference that I called your attention is this book by Ivezik et al. Called Statistics, Data Mining, and Machine Learning in Astronomy. Željko Ivezik is the PI of LSST. He's a very known astronomer. Everybody here are very known astronomers. And this book has a site, and they have a software called AstroML that has lots of programs in machine learning, very useful for astronomical tasks in general. You may find softwares already done that can be applied to your problems in this book. For machine learning algorithms, I suggest the book by James Vitor Hassan Sibirani, Introduction to Statistical Learning. This book is available online, and is very useful to understand how some complex machine learning algorithms work. Because we adopt, say, a practical approach in the sense that we use sometimes the algorithms without knowing how they work. But since you are working with a given algorithm, it's important to know at least the basics of how the algorithm works. So this book provides a good introduction. Well, there's a very famous book on deep learning by the fathers of deep learning, Goodfellow, Benjamin, Purville, that is available online in many languages, certainly also in Spanish. My Bible is this book here, Deep Learning with Python, by Cholet, who works in Google. Okay, this book is available online with all the programs, and it was with this book that we and our group in São Paulo learned machine learning, deep learning in particular, because this book is focused on deep learning. And there are other books here that are also useful. I just call your attention for this book here. The theory that would not die. How Bayes' rule cracked the Enigma code, hunted down Russian submarines, and emerged triumphant from 2 centuries of controversy. This is a book for lay people. It's not a book on mathematics at all. And it describes the history of statistics and of Bayesian methods in general. And you reading this book, that is very agreeable reading, you will be able to understand why there is such a controversy nowadays between frequentist and the Bayesian methods. Okay, I stop here and pass the laptop to Vitor. If you have any questions. Any questions? Okay.
Questions? No?
Can I start? So, hi everyone, it's Vitor again. I'm going to go through the practical concepts in this class. And before we starting, I just wanted to add to what Laerte said before, that the Astronomy book from Embedding is available as a Python package. So you can install it in Jupyter Notebook, for example, and use the examples they have there. It's very good. And another thing that I wanted to talk about is just point out that in Monday's class, someone pointed out about the way that I was minimizing the neg likelihood, and it was the person was correct. So you don't need to estimate the sigma. You can only estimate the two parameters. And I corrected in the notebook, so if you open it again, you see the change. And in today's class, we will talk about what Laerte said. So we will talk about the kernel density estimations, about Gaussian mixture model very briefly, about k-means, and about principal component analysis, the PCA. So let's start with kernel density estimations. So it's quite common that we have some, so as Laerte presented before, it's quite common that we have a distribution of data that simply doesn't fall into any kind of distribution, any single distribution that we are familiar with. So for example, let's say that it doesn't fall into a Gaussian or a Poisson distribution or any other kind that we are like the known probability distributions and the classified ones. So a good way to, if you want to try to estimate the probability distribution of the data, you can try to use kernel density estimation. So in this case, just to, I think it's easier to see this happening instead of trying to explain the concepts behind it. So what we'll try to do here is to apply kernel density estimation to some normal data. So I'll try to generate 10,000 Gaussian points, and with a mean of 0 and a sigma of 1.4. And so I will use the same functions that I used in the class before. I try to be as cohesive as possible between the notebooks, trying to use the same function so you don't get lost. So I'll use the same function that we used before to generate the normal points. And then we're going to shift some amount of the points. So we're going to take 70%, so the points that are further than 30% of the data, and we will add 5 to the distribution. So this means that our random sample, instead of being a single Gaussian, it will have 2 peaks. So you will have a peak in 0 and a peak in around 5. And so this way we have like some kind of distribution that we know that is, by looking at it, it's probably made up by 2 Gaussian distributions. But is there a way to easily and non-parametrically estimate the distribution? And yes, there is, by using KDE estimations. And so I'll just go very quickly go over through the equation that Laerte talked about. So to estimate the probability density at a point x in a d-dimensional data space, there is this equation over here. So 1 over nh by d, and the sum of the kernel function. So k is the kernel function, h over here is the bandwidth, and d is the distance between the point, and xi, and n is the number of points that I'm trying to estimate. And so this means that the probability density is simply dependent on the amount of points that there are in that space, in that range that I'm defining. And so each one of these components in the equation means something different. But especially, we are especially interested in two of them: the kernel function and the age, the bandwidth. And so the kernel function is trying to dictate some kind of distribution to take as the basis. So the kernel function in this case can be, for example, a Gaussian, a uniform distribution, another Poisson distribution, and the age, the bandwidth, will try to give you an idea of the resolution of the distribution. So the lower the age, the more let me remember if it's one way or another. So the lower the bandwidth, the higher the resolution of the estimation. So you can see that in action. I'll try to connect my computer here just to show you how it works in practice. So let me run this notebook so we can see this in action. So to do that, to estimate the KDE distribution of a function, of a data set, we can use a very simple a class called the kernel density that comes from the sklearn neighbors library. So to use that, it's very simple. So you just need to reshape your data if it's one-dimensional, which is our case. If you don't do that, it will give you a warning or an error. I don't remember which one, but it will say to you, oh yeah, you need to use this reshape function here to pass data. So you don't need to worry if you forget. The program will remind you. And the kernel is fit. So to use the KDE itself, you need to give a value of the bandwidth. So in this case, we use 0.5. And then we need to give a kernel distribution, which a kernel function, which in this case will be a Gaussian. And then we need to fit the data that we have into this kernel density estimator. And after we do that, it's very simple to try to get the distribution again. So now the kernel density has a kind of like a probability distribution function that you can work with. And so to get some values and to plot this distribution, we use the score sample method. Oh, sorry. We use the score sample method to just to plot these values. And so the score sample method gives us the log of the likelihood. So to get the density, we need to just exponentiate the values. So here somewhere I go through so I take a lot of samples from the x-axis, and then I take the score samples, the values of the distribution. And when I plot this, you see that I'm plotting both the original histogram and the distribution that the KDE obtained. And you can see that it fits very well. And if I change the parameters that I defined before, so let's say, for example, that let me just change this, for example, I'll change to 0.8. And you will see that the results here, the histogram should change to, let me see, okay. So there is it change as well, the distribution. And you can change the values, you can change the age to whatever you like. And there is a method for you to find the best age, which is what Laerte told about when you that you can use the cross-validation. So I try to link, if you want to work with kernel distributions, you can check out how to do kernel estimation with cross-validation by clicking on this blog over here. So it will go step by step on how to do this cross-validation. And I think that gives you the general idea of what the kernel density estimations do. So I think we'll move to the next part. I'll talk about k-means. So as Laerte said before, k-mean is a very well-known clustering algorithm. Let me just, oops, okay. It's a very well-known clustering algorithm that tries to estimate the clusters, k-cluster of objects, by seeing the distance between them. So in this example, I think so we're going to use some real astronomical data. So this is some data that was actually published in arXiv, I think a few weeks ago. So it is by these authors, Fabrícia Oliveira, and she used some clustering algorithms to separate two different groups of stars. So the blue horizontal branch stars from the blue straggler stars by seeing their surface gravity. So and again, this is some real. They actually use this data in the paper. So to the first thing that to go through this example, the first thing that we need to do is just download the data. So place the data in this notebook. And in this case, since Jupyter Colab is running on Google machines, I use this command over here, so wget, which is a shell command, to download the data from a Dropbox that I created. So if you click on the files here on the left, you see all of the data that it has downloaded. So the one that we're going to be used here, the BHB and blue straggler stars, and the others one that is going to be for the next sections. And so, okay, so downloading after downloading this this data, we can try to read this table by using a pandas function. So if you go back in one of the notebooks that I shared with you was the called tools notebook, has an explanation of how the pandas library works. So you can go back to that and check how to read CSVs or something like that. So we can easily read the file by using this function read CSV, and then we can just print the top 5 rows by using the head method over here, just to see what our data set has. So we have a few columns. So each line represents a different star, and the first column is the right ascension, and the second column is the declination. So just positional arguments, just to see the stars in the sky. And then we have some 4 different log G. So the first one, the log G is what we call the surface gravity of the stars, and after what is the underscore is the method in which the log G was calculated. So the first log G was calculated by this method, the ANNRR, which is a neural network method. And we have the associated uncertainty of this method. And we also have the log G estimated by a spectroscopic method that I'm not really sure how they estimate it, but it's described in the paper if you want to check. And we also have the uncertainty associated with this log G. The idea behind this data is that usually the blue horizontal branch stars are separated from the blue straggler stars simply by a log G cut. So for example, for log G below a certain value, it's something, and log G after a certain value is another population. And so what they're trying to do in this paper is trying to have a better grasp of what separates these two populations by using 2 different log Gs obtained by different methods. So let's plot this log G to see exactly what are we working with. So this is the oops, let me try to make it okay. So this is the surface gravity for both the ANNRR method and the SPEC method. So I just simply plotted the values on the table. So on the y-axis the SPEC method, and on the x-axis the neural network. And you can see that each star is separated into you can kind of see 2 blobs of data points. So you can see one here and one here, and each one of them corresponds to a different population. One is the blue stragglers, and one is the blue horizontal branch. And the idea is that by using this method, you can have a better idea of how these populations are separated, not by just cutting the log, the surface gravity. And so we're going to use two methods to try to separate them. The first one is going to be the k-means, which Laerte talked about, and another one is going to be the Gaussian mixture models, which Laerte also mentioned. So to use the k-means, it's very simple. You need to, I think, okay, I start here. So the k-means is a clustering algorithm that's going to separate between a predefined number of clusters. So in this case, we're going to separate the data into two groups. So this is defined by the, so we're going to use the k-means function from the sklearn.cluster library. And when we initialize this class, we need to give the number of clusters that we want. So in this case, we're going to want simply two clusters. And then we fit the data to the k-means algorithm to see the separation. So we're going to fit the data based on the log G of the ANNRR method and the spectroscopic method. And all right, so after the function fitted the data, we're going to simply plot this new separation based on the labels it gave for each one of those stars. So each stars in the data that I have now has an associated label that k-means gave me. So it is either 0 or 1 depending on which group it is part of. So let's plot the separation, and you can see that I'm coloring when I'm plotting the data, I'm coloring the data based on the k-means labels. So each star here is colored based on the k-mean output. And you can see that it actually managed to separate the groups pretty well. So you can see that the main center of the groups are where we expected. So there is this blob over here and this blob over here. And there is this kind of line here that is hard to see on the projector, but it's easy to see in our computers, that is trying to separate the two distributions. And you can see that this line over here is not neither a horizontal line nor a vertical line. So it is not, for example, trying to separate only based on the single cut from one of the surface gravity. So for example, it's not trying to say, oh yeah, so every value over 3.6, for example, on the log G spectroscopic method is from one of the populations or the other. Here, by using this 2D method, you actually have a better grasp of how each star is present in each group. And I think this gives you a very good idea of how the k-means method works. Okay, so it worked pretty well. Now let's see how a Gaussian mixture model will perform. Gaussian mixture models are usually a higher level algorithm, so they are considered usually better than the k-means, not simply because of the performance it can have, but it also can help us to give an idea of how the probability of each member of the group separately. So it can say, oh yeah, this star, for example, has a, I don't know, a 50% chance or a 60% chance of being in this group, and the other percentage being in the other group. And so it's a very useful algorithm. So to use the GMM, we're going to use the same dataset that I described before. So we already have it downloaded, we already read the file. So we simply need to place the algorithm itself. So for the GMM, we're going to use the sklearn mixture library and the Gaussian mixture function. Remember, if you are not sure what function or what library to use, simply Google it. So just go in Google and say, oh yeah, how do I get the Gaussian mixture functions in Python? And the first result will probably be the sklearn mixture Gaussian mixture function. And so to initialize it, we do the same way. So we need to, in the Gaussian mixture case, we need to tell it how many Gaussians it has to fit. So in this case, we're going to fit two Gaussians. So we have two components. We have two Gaussians that are going to be fit. And Then we're going to fit the data the same way that we fit before, and we're going to obtain some labels for each one of the stars in this case. So I'm using here the fit predict method, which will first fit the data and then predict the labels after fitting the Gaussian mixture algorithm. And once it's fitted, we can plot. So I'm going to use the same way that I did before. It's just a copy paste of the code, but I'm changing the color to be the GMM labels that I described before. So each point, each star is going to be colored as the GMM separation. And you can see that the result is very similar. So the GMM model and the k-means model are actually pretty similar. So just to show you a comparison. So here is the k-means. You can see that it goes a little bit further, and the GMM goes doesn't go that far into the separation. But so each model is performing more or less similarly. But again, the great advantage of the GMM separation is that you can actually get the probability of each star being a member of each group. So you can know, for example, this star over here, what is the probability that it is in this group and this group? It probably be around 50-50. But you can actually know that by looking at the probabilities. I didn't include the probabilities here because I thought it would be too much to talk about today. But you can check online. You can search for example, how to obtain the probabilities from the GMMs. And you have some very good notebooks explaining how to do that. And I think this describes overall what I wanted to show you. You can see that by looking at this method, you can successfully separate the two groups by using either the GMMs or the k-means algorithm. Both of them took around the same time to train. It was very quick, so you don't have to worry about that. Now, the next thing that I want to talk about is the principal component analysis, the dimensionality reduction algorithm. And I'm going to, this is the last thing that I want to talk about. This is a very extensive part of the notebook. So the principal component analysis, as Laerte told us before, is a dimensionality reduction algorithm. It tries to represent the data with fewer components instead of spreading the information around each feature. So in this case, let's look at an example. So let's consider, for example, spectral analysis. Let's say that we want to study the spectrum of some objects, which have, for example, let's take the spectrum between 3,500 angstroms and 6,000 angstroms. If we try to, let's say that we want to have an algorithm perform on the spectrum, on this data, if we try to pass this information, the whole spectrum, to the algorithm, it's probably going to take a lot of time to train. So because of the amount of data that the amount of data that we're passing to the algorithm, it's going to overload the algorithm. It's going to take minutes up to hours to train this model. And so an option to do is let's see if we can manage to give the same amount of information to the model by not using the full range of data itself, but a few principal components. So a few some other amount of information. So let's reduce the dimensionality of this data. Instead of giving the algorithm to 2,500 data points, we're going to give just a few and see if it works. So to have this dimensionality reduction, we're going to use PCA, so principal component analysis. And in this example, we're going to use a data set of 100 synthetic spectra that was done by an analysis by Ariel Wedley and some other collaborators. What they managed to do was so they combined the SDSS spectra with the galaxy photometry to obtain some state-of-the-art spectra via, so there is this code called Starlight, which is an SCT fitting, so a spectral energy distribution fitting code, which basically tries to fit have a whole range of the spectra by giving it some information. So basically, just to summarize, we have now 100 galaxies, and these galaxies have, for each galaxy, we do have the spectral information. And so the first thing that we're going to do, I'm going to plot one of these examples just to make it clear. But the first thing that we need to do is just download the data again, the same way that we did before. And I think this data is, so I passed Analia this data, so she can upload in the website. And I think she uploads. So if you're running this locally on your computer, if you download this notebook and run it locally, you don't need, of course, to download the data again. You can just go to the next cell. So let's read this catalog by using the read CSV method the same way that we did before. And so we're going to use the read the 100C. There are two files. If you download this, if you run this notebook directly, all of the cells, you see that there are two files over here. The one is the 100C, and the other one is the 100CL. So these are different. The first one is going to be used in the example. The second one is going to be used in the exercise that I gave you below. So let's read this data and see what it has. So the first column is the lambda column. So it basically is saying what the wavelength is. And the other columns, so there are 100 stars which are placed in the columns over here. And each line is representing a flux of the spectrum. So let's plot one of these galaxies, one of these spectrums, just to see what is going on here. So we will separate the lambda from the other data just to make things easier going ahead. So we will call it the wavelength data, and then we will drop the lambda column from the data frame itself. And then we will transpose just to make sure that the galaxies are on the line. So each line represents a galaxy, and each column represents a different wavelength value. So let's plot the spectrum to see how it goes. So we'll plot the first spectrum. So you can see that I'm using the iLoc, which is the item location function. So it basically is getting the very first line of the data frame, and you can see that. So on the x-axis we have the wavelength, on the y-axis we have the flux, and you can see that it's a very common spectrum. So usually what you would see when you will look at a spectrum. And okay, so but there is a lot of information. We remember that each point over here, so we have 2,500 points. That's a lot of data to try to pass to an algorithm. So let's apply PCA in this to this data. So before applying PCA itself, before going through the algorithm, it's very important that you escalate your data, so that you scale your data to make sure that everything that you're working with has the same range. So each one of your features has around the same range. So PCA is very sensitive to different ranges of data. So if you pass, for example, try to pass the whole spectrum, you see that, for example, some wavelengths, for example, will fall between some range different from other wavelengths. So we need to make sure that those ranges are the same. And so we use what we call a standard scaler. So the standard scaler is basically a way to make sure that all of your features, in this case, every wavelength flux, is falling into a Gaussian. So it will try to transform the data into a Gaussian distribution that is has a mean equal to 0 and a standard deviation equal to 1. So after scaling, this will be very common in the next two classes. You see that for, I think, all of the machine learning and deep learning examples that we go through, we need to scale our data. It's very important, this step. And we will also be checking in the later classes for cases, for example, for missing data, and for data that are out of the range of the range that we want to be working on. But in this case, this is a very simple data set that is working very well. So don't need to worry about that. We will worry about it in the next two classes. So let's feed the data to this this scaler. So basically, this variable right now, the scale data, will basically be having the same information that the spec data has, so the whole spectrums, and but it is transformed into the scale data. So it's now scaled. So now let's apply the PCA. So the PCA is going to be the function from the sklearn.decomposition library. And to create the PCA, we need to, first of all, create the model. So we need to say how many components our PCA will have. In this case, I chose 10 components, but you can choose any number that you want. You can choose up to the number of features that you have. So in this case, you can have as many components as 2,500 components. But 10 is already enough, so we'll be using 10 components, and you will see that after the third component, there is no need to worry. So let's fit the PCA to our data. Here is the linear algorithm that's going to be applied that Laerte talked about before. So now the model, the PCA model, will fit the data and actually work with, go through all of the principal components and find each principal component. Once it's fitted, we can look at the what Laerte called the, I think there was a plot that Laerte showed, that is the variance ratio. So we want to see the variance ratio of each one of the components. So to see, for example, how much of the variance is gathered around the first principal components, the second principal component, and so on. So in this cell, we basically we are just gathering the explained variance ratio information, and then we plotted after some. I just tried to write this so it's easier for us to plot and show and print the results. So, and you can see that for the first components, we have almost 90% of the variance is explained by these first components, and the second component is just, I think, 8% or 5%, sorry, of the data, and the third component is 3%. And as you go further into the principal components, the less useful they become. So the last few components, you can see that they have very little impact on the variance. And this is important because you can see that, so basically what this histogram is describing is that most of it, so the principal components analysis managed to convey the information just in the 90% of the information of the spectrum is only in the principal component. So the principal component, the first principal component, is describing almost 90% of the variance. And so let's see if this works in practice. Let's see if we can recover the information from our spectrum only with the three principal components. So before doing that, just to show you, one of the very nice things that you can do with PCA is studying the latent space, what we call the latent space, which is when we plot, for example, the PC1 versus the PC2 of each data point that I have. So for the 100 galaxies that I had previously, you can see that in the space of the principal components 1 versus the principal components 2, they don't have like any shape, or there isn't any structure that you can see. You can kind of see that there is, for example, like a linear kind of distribution, but there isn't much things that you can say about this distribution itself. But if you use, for example, if you apply this data to data that is clustered, for example, if you try to apply the PCA, for example, for the data that I showed before, so the groups, the different groups here of stars, maybe in the latent space, you will see some separation of the groups. So in this latent space, the PC1 versus PC2, you will actually manage to see two different groups, for example, and you can actually study the data in this latent space. This is a very important part of any dimensionality reduction algorithm, is studying the latent space. In this case, since we didn't manage to see any structures, we'll just try to recover the information about the spectrum with the first three components. So to do that, we're going to, the PCA method has a method called inverse transform, which is basically trying to go back, so from the principal components, go back to the spectrum itself. And so what we're going to do here is we're going to take the principal components of all of our spectrums. So in this case, we're going to apply this for just 4 different spectrums. So the spectrum number the first spectrum, the spectrum number 25, the number 50, and number 75. You can change these values. It's just I picked at random these spectrums just to show you a comparison. And then you will want to, what we did here was that we took the first 3 principal components and then we zeroed out the other components. So that's what this line of code over here is trying to do. So it's trying to gather in this PC spectra variable, it's going to append the spectrum of the 4 galaxies that I picked, and you try to get only the first 3 components, and then it will zero out the other components to see if you can recover the spectrum just based on the 3 first components. So let's see if you can manage to do that by using the inverse transform function. And so we also need to, after doing that, we also need to scale the data back. So remember that we scale the data to go through the model. When the model gives us an inverse transform, it also gives a scale, some scale results. So we need to also apply the inverse transform on the scale data. So to obtain the spectrum that we actually want to see, not around the 0 and 1 mark. So after doing that, we have some very interesting results. I think it's very hard to see on the projector, but you can see that. So the red line is the original spectrum, and the blue line, which is very transparent, I tried to make it transparent, is the fitted, the recovered spectrum from the PCA. And you can see that, for example, for this first spectrum, the PCA works very well. You can actually see that there is very little gaps between the original and the recovered spectrum. And you can see that for the other ones, it managed to, especially for the visible part of the spectrum, it manages to recover it very well. So you can see in this the second spectrum that there are some gaps over here on the bottom, but the overall spectrum is recovered, especially for example, the absorption lines of the spectrum are recovered. And you can see that's also in the third spectrum and the fourth spectrum. Each one of those I picked randomly, and you can see that just with the 3 principal components, you can actually gather back the information about the spectrum. So the idea is that instead of giving your model the whole spectrum, you can actually give just the 3 principal components, and you will have the same information as if you gave the spectrum itself. And I think this covers most of what I want to talk about PCAs. I think that's very clear, but just to remember the main points, you usually want to apply PCA if you want to, for example, have a dimensionality reduction in the case of recovering data, or in the case of what I talked before, if you want to study the latent space by clustering or whatever you want. And I left you all with an exercise. So the file, so the other file that I presented here is which is this one, the spec 100, sorry, the CL data. I don't know if you can manage to open that, but usually in Colab, if the data is in a .csv, oh no, you cannot. You can try to open data over here. We'll show you a table of the data. But anyway, so the difference between these spectrums, it's the same 100 galaxies, but this spectrum, instead of just having the absorption lines, it also has the emission lines. So what you wanted to do is the first thing that we wanted to do is to examine the data by plotting some spectrum. So plotting, I don't know, the first 4 spectrums, then verify the most important spectral lines covered by the spectra. So you will see that some of the spectral lines will be very common in different spectrums, and we want just you to have an astronomical idea of which lines are important. So after that, we want you to apply a PCA analysis and verify how the variance ratio associated with the first 3 components, so basically this histogram right here, how it changes compared to when you have the case with emission lines compared to the case without emission lines. And then we simply want you to examine the spectral reconstruction with only the 4 principal components. You can try with 4, with 3, with 10, whatever you want. But we just want you to have a grasp of how to reconstruct the data. And here is a small snippet just so you can download the data with the CSV, and then you can start doing our exercise. And I think that's it.
Questions? If you're still here.
I would like to make a comment about this PCA exercise. We have a spectrum with 200 and 2500 wavelengths. So one spectrum may be considered a point in a space of 2500 dimensions. Okay, and we are projecting, in the case of the exercise, in a space of 3 dimensions. You can see the degree of compression that we obtain in this case. And another interesting exercise is for you to see how change the form, the reconstruction of the spectrum using, say, just one principal component, 2 principal components, 3 principal components. And you see, Vitor showed the result with 3 components. But it's amazing how well it works, PCA, yeah? At least in this sort of problem. Because you are able to reconstruct a very high dimensional space with just 1, 2, or 3 numbers. This is really impressive.
Another, just to add to that, sorry, we can actually use the other dimensional reduction spaces. So if you want to try your hand at TSNE, so the T's that Laerte talked about, you can actually try. You probably arrive at the same kind of results, but it's actually nice to compare this dimensional reduction algorithm. So, question?
A ver si me ayudan. Hay que pasarlo para allá.
Hi, I try to speak in English, but
No problem.
my English is no good. Can you see the formula to the PC1 and PC2 and PC3?
I think you can from the library. I didn't try to see, but if I'm not mistaken, you can actually see that. To check that, you can actually go to the documentation of the where it is. Okay, here. So if you go to the sklearn decomposition.pca documentation, you can actually see all of the methods that it has available. And I think one of them, Laerte? And I think you can get the equation from that, but I'm not really sure. You need to check.
Actually, PCA itself is not an equation. You need to solve for the eigenvalues of the covariance matrix of the data. And the PCA are the eigenvectors of the covariance matrix. So it's not an explicit equation, but it's a kind of a linear algebra problem that is solved by matrix multiplication, things like that. No, the numbers, of course, the values of the principal components you can see. This is the result of the method. But it's not a formula for the first component. or second component, things like that. I don't know if I understood your question.
Any other questions? Ok. Entonces agradecemos a Víctor por la clase de hoy. Y los invito a sumarse ahora a 12:30 al seminario de la facultad, donde Vitor nos va a contar cómo aplica el Machine Learning a las investigaciones que está desarrollando dentro de la colaboración SPLAS. Así que bueno, nos vemos mañana a la tarde. A partir de las 14 nos juntamos acá de nuevo.